Here we go, centripetal force. So we've done centripetal acceleration already. So we're just going to add a little mass. And we have centripetal force. Okay, here's a previous equation. And as you can see, it's really quite simple. It talks about the acceleration of any body which is going in a curved path. And basically, the centripetal acceleration is equal to the square of the velocity. So this is the tangential velocity going around the circle, divided by the radius of curvature. Now, this is very important because you can be on a curve and still not be on a completely closed circle. Essentially, this is like putting a tangent line on a path. You're actually fitting a circle to that path. Whatever the radius of that imaginary circle is, that will be this r right here. So if you're in a tighter turn, that r is going to be much smaller. And as you can see by that equation, r being in the denominator is going to make the acceleration greater. Okay, so that is, again, just a quick review of centripetal acceleration. Now, here's a very popular ride. These are, they come in a number of different names. I think the last time I was to a state fair or a county fair, we called these things the gravitron or something like that. But it's basically a rotating drum where from the movement of the drum, you're stuck up against the wall, and essentially friction holds you up, whereas gravity is going to pull you down. Now, basically, the way that this works is that some of the forces are real, and we can analyze them in terms of weight and normal force and friction. And some of the forces are fictitious, which means we feel like those forces are there, but they're not. So here we go. Clearly, you can see that you've got gravity, which wants to pull you down. Okay, that's shown right here. You have the normal force from the rotating drum, which pushes you to the center. That's the centripetal force. And then you have the frictional force from the normal force, and that's preventing you from sliding down. So it's kind of a cool ride. It has you stuck to the walls, and it can do that because it's essentially using friction from the normal force, from the centripetal force, to keep you up on the wall. Of course, this is not the way that we feel it, okay? The way that we actually feel it is somewhat different. We feel like we're being pulled to the outside, but that's not actually the case. It's really our inertia that wants to keep us going in a straight path, but the normal force from the sides of the wall push us inward. That's the action. The reaction is that we push back on the wall, and that's what we feel is this fictitious centrifugal force. It doesn't really exist, but it feels like it exists. Okay, so perceived forces, centrifugal force doesn't exist. That's actually us pushing on the sides of the wall. And we'll talk about that more later on. And then, of course, we can feel gravity trying to pull us down. Okay, let's do some more. Roller coaster loops. Loops accelerate you downward with an acceleration greater than gravity. So you actually feel weightless. Here's how this works. And this is a little bit subtle in terms of how it works. Gravity wants to pull you down. Okay? Gravity's always pulling down, it's always there. But when gravity becomes the force that keeps you on this curve, what happens then is that you actually feel weightless. Because if you're accelerating with gravity, you're technically in free fall. So the weird thing is, at the top of these loops, you are actually almost in free fall because gravity is pulling you down. When you're at the bottom of the loop, it's a little bit different because not only is gravity pulling you down, but you need even more normal force. Okay, if gravity's pulling you down with, let's say, 200 newtons of force, you need 400 newtons of normal force to compensate not only for the gravitational force, but the extra centripetal force that you can experience. So it's kind of cool. You feel, very light at the top of a loop. You feel very heavy at the bottom of the loop. And this is because of the direction of the normal force. If the normal force goes with the gravity, you feel lighter. The normal force acts against gravity, you will feel a force, perhaps many times the acceleration of gravity. Okay. And again, here's, ever wonder what it's like what a bicycle tire feels like? Well, go on one of these rides. Again, if we take a look at this, we can see that the force here is toward the center. So there's your centripetal force. So when you're at the top here and gravity's working with the centripetal force, you feel lighter. When you're at the bottom, I can't show a bottom, the centripetal force is working against gravity and you feel much heavier. So a little amusement park physics here to show you how this works. Well, let me go on unless I get rid of the annotation tool. Okay, here is one of these old-fashioned swings. They're sometimes called a Black Forest swing. And I don't know if you've ever been on them. They're pretty common. You've got this rotating top, which attaches to these swings. And the swings will basically connect to the rotating top via some sort of chain or cable or set of chains. And that creates a tension, which is off in this direction right here. Okay? So you have the tension pulling you to the center and upward, and that's countering the weight downward, plus providing a total force toward the center. Now, again, this is a little bit hard to conceive. It looks like this object or these people on the swings, they're static because they're just going round and round and round. But remember, they're going around in a circle. If you're constantly changing your direction, you're constantly changing your velocity. If you're constantly changing your velocity, you're accelerating. Okay? So to keep these people accelerating, there has to be a net force into the center. Okay, let's go on to the next. Airplanes. Anytime an airplane banks, it uses its lift. One would think that it turns like a car. In a car where you turn the steering wheel and that turns the tires. In a plane, they do have a rudder, which will actually change the direction that the nose is pointing. But that's not an effective way to turn. You'll actually get the plane flying sideways a little bit because those aerodynamic surfaces don't really steer it the way that the steering wheel and the wheels will steer a car. So to make a turn, what a plane actually has to do is actually has to rotate, okay, along its long axis, okay? We call this a roll. It does a little bit of a roll. And when it does that, what that does is it puts the lift, which is normally straight up to act against gravity, it angles it just like the chains on that swing we talked about, okay? So the harder you bank your turn, okay, the greater the amount of acceleration and force is going to be toward the inside of the turn. That'll allow you to turn faster. Now, the problem is you've got to execute these turns. You have to execute these turns such that you're still opposing gravity. Gravity's pulling down. You still need enough upward force or vertical force to compensate for that. But of course, if we look here, the total lift is much greater than the force needed to go against gravity. So much of this force goes not into an upward force against the weight. We still need that there, otherwise we fall out of the sky. Most of it goes into making a tight turn. And if you look at this, it appears that this orange vector is, which is the lift, is approximately 3 times greater than the weight. So in that particular case, a person sitting in the cockpit would experience 3 Gs of acceleration. And you get the same thing on a roller coaster. When you go down and through a tight turn, that large amount of normal force, now the lift is providing what would have been the normal force on a roller coaster, that gives you the sensation of being much heavier than you are. So, I always found that very interesting that you couldn't just turn, like you do in a car. You actually have to rotate the whole plane to execute that turn. And again, you can see the vectors. Here's a commercial airliner. You're not going to make high G turns with this. And you know, generally they bank, but the amount of lift is, maybe increases it to 1.3 Gs, 1.4 Gs. Two things. One, they don't want passengers to be uncomfortable. And also, remember where the lift is coming from. In a high performance jet, there's a tremendous amount of strength in the wings because it's made to undergo, a force of 10 or more Gs. Okay, it can do these high speed turns where the wings can support 10 times the weight of the actual aircraft. But in a commercial aircraft, they're not really made to do that. Literally, you could tear the wings off of the plane if you created too large of a lift. So they're limited in how much they can bank their turns. Okay. What about circular motions on the Earth? Well, how does that work? The Earth is rotating on its axis. So actually, you feel lighter at the equator than you do at the poles. It's a twofold reason. One, the first reason is, and I'm going to over exaggerate this, is the Earth is not round. Okay, the Earth is actually what we call an oblate spheroid. Slightly bulges more at the equator than it does at the pole. So if you measured the distance, the diameter from one side of the equator to the other, you get a larger measurement than you would from pole to pole. Now, you can't see this in photographs. It's very, very subtle, but it does mean that gravity is slightly less at the equator than it is at the poles. The other thing that's happening here is, remember that, feeling weightless? Well, in this particular case, you have your two basic forces again. You have gravity pulling you toward the center of the Earth, but it's also providing some of the centripetal force that you would be experiencing on a rotating body. So it's not that gravity is so much less at the equator. It's more that some of the gravitational effect is subtracted off for centripetal acceleration. So again, it's like feeling lighter at the top of a loop. Gravity's still there. You're no lighter than you were before, but because you're accelerating in the direction of gravity, and here gravity is accelerating in the direction of the centripetal acceleration, that makes you feel lighter. Okay. And again, we can actually calculate this acceleration. It's very, very small. The acceleration of gravity is 9.8 meters per second squared. Here, you only lose like 3/100ths of a meter per second squared. So the effect at the equator due to the centripetal force is actually about 1 in 300, 1/300ths, about 0.3%. So not a really big effect. If you want to lose weight, yes, you can go to the equator. but you're not going to lose very much weight. It'll be, once again, combining all the different effects, maybe 0.5% of your weight will be less. Not worth making the trip. So if you were 150 pounds at the North Pole, you'd probably be about 149.5 pounds at the equator. What about the Earth traveling in orbit around the sun? Well, actually, that centripetal force we never feel. If we're moving with the acceleration, and this is part of Einstein's theory of general relativity, it's as if we were accelerating at that rate anyway. So again, we're not going to feel it. But calculating it, the Earth accelerates about 0.006 meters per second squared, even if that effect we're subtracting off from our gravity. It wouldn't be significant. Now, we can actually create an effect comparable to gravity in space using normal force. Here's a rotating cylinder. This is a cylindrical space station. And one of the big problems that astronauts face in being in space for a very long period of time is the lack of weight makes your muscles atrophy, makes your ligaments and tendons become weaker, and reduces the density of your bone. Your body's basically greedy. If you're not using it, you lose it. So astronauts returning to Earth, when these first long duration missions occurred, they couldn't even walk when they got back to Earth. They became so weak. So NASA started working on a way to keep astronauts exercised in space. And it's not really easy because you've got to spend a long period of time doing not a whole lot of exercise. They'll strap you into a treadmill. The straps will create the normal force and will help, increase some of the response that your skeletal muscular system will have. But astronauts still come back weaker. The ideal case would be to rotate a space station. We can't do that with the International Space Station because it's not strong enough to withstand the rotational effects. And also, you'd have to keep rotating the solar panels. So this hasn't been incorporated into any space stations yet, but we see it a lot in fiction. We saw it in 2001, The Space Odyssey. This is a film that came out in 1969. So pretty much during the beginning of the Apollo missions to the moon. The Apollo missions had gone on before that, but they were still test missions. They hadn't gone to the moon yet. So 1969 was released, same time that Apollo 11 landed on the moon. And also other space habitats have been proposed where we'd have these rotating rings. Now, a movie I highly recommend is Elysium with Matt Damon. That's sort of a futuristic dystopian movie where the rich go into this opulent space station that rotates and provides, sort of this utopia for them, and everybody else is poor and left on Earth. And it's an analogy to many of the problems that we're having right now, where we're getting a very large stratification in society. So this is sort of a dystopian taking that to the extreme. It's commentary on a lot of healthcare problems, but it does do a good job with the physics for a rotating space station. Now, I just want to go over something quickly before we go into the calculations from this movie. And what we see here is our original centripetal acceleration equation. But if we replace V with omega R, omega is something that we're going to talk about more later on. Omega is the angular frequency, and it's how many radians per second you rotate. If we replace it with omega R, up in the numerator, we get R squared omega. One of the r's cancels out with one of the r's down here, and now our centripetal acceleration goes by r times omega squared. Okay, how many rotations? I'm sorry, 2 pi radians per second is omega. If it's 1, that's normalized. I need more coffee. All right, so again, in this movie, here you have this beautiful space station up in orbit where all the rich people live, and basically this rodent planet beneath, which has been polluted and just is not a nice place to live. On top of that, they have androids that basically keep everybody in line, and just not a great place to live. So Matt Damon, growing up on Earth, strives to get to Elysium because he's injured in some accident at work, and he's given a fatal dose of radiation, and only up in the space station is Elysium can he get the cure. So the whole movie is him trying to get up there. I won't ruin the end of the movie, but I got the specs from the movie, how big it was. This space station was supposed to be 34 kilometers in radius. And so I did a little calculation. Well, what do we need to get an acceleration of 9.8 meters per second squared on the station? So here's my original equation. So I'm going to solve for omega to see how fast this thing needs to be spinning. So omega is equal to the square root of a over r. There's the acceleration, there's the radius. And it would only have to be rotating about 0.017 radians per second. We divide that by 2 pi and multiply that by 60, we get about 1 rotation every 6 minutes, or about 0.16666 repeating RPMs. Okay. Okay. So centripetal acceleration, it's the acceleration toward the center of a curve. If you want the total acceleration, you actually have to take the combination of tangential acceleration, speeding up and slowing down, with a centripetal acceleration. But we really don't do a lot with that. Basically, it's the same thing you need to do, combining the x and y components of anything. When you have two perpendicular directions, the tangential direction is perpendicular to the centripetal direction, you're going to get, or you're going to need to do the square root of the sum of the squares. Once again, centripetal force, F equals ma, that just comes from Newton's second law. We just take the centripetal acceleration and multiply it by the mass. And the centripetal acceleration could be provided by tension. It can be provided by the rails on a roller coaster track. It can be the tension from the chains in that Bavarian swing. It can be the force due to friction. It can be even gravity. All of these can provide the force, which becomes a centripetal force. We're going to do an experiment with this. We're going to take a pendulum. It's going to swing back and forth on a circular path, be able to calculate the centripetal force from this. Okay, so the general equation is that Fc equals mac, mv squared over r, if we combine mass with our acceleration equation. And the strategy is really the same of what we've done previously. Draw a free body diagram, choose a coordinate system, but you want one of the axes to point in the direction of the centripetal force. So be very careful when you do this. The net force is always toward the center of rotation, and we're going to use Newton's second law. Fc is equal to mac, which is equal to mv squared over r. So all your forces add up to that mv squared over r. Solve for your unknowns. Now let's look at a few different examples. This first case is going to be a level curve. Then we're going to look at a bank curve, and see how we can take some very familiar forces and some familiar situations and turn it into a situation where we're going along a curved path instead of a straight line like we've done before. Here's a real simple one. We have this car. Gravity pulls it down, the normal force pulls it up. And when we steer, okay, we turn to the left, we're going to go around a curve. So the centripetal force is to the center of that curve. So really the friction from our tires is providing that force that keeps us on the road on this curve. So again, the sum of the forces is equal to mv squared over r. There's only one force here because weight pulls down, the normal force pulls up. That is friction. All the other forces cancel out. So I set my friction equal to this. Friction is mu n. The normal force is the weight. So here's my equation right here. So once again, the total force, friction, is equal to mv squared over r. All right. How much friction do I need to stay on the road? Well, mass cancels out on both sides, so I get this equation right here. I divide both sides by g, and this tells me that the coefficient of friction required is equal to v squared, speed that I'm going around this turn, divided by the radius. The tighter the turn, the more friction I need, and also divided by g. So what this means is, in bad weather, my V's got to be slower because my coefficient of friction is going to be lower, okay? In good weather, my coefficient of friction becomes greater, okay? So let's say we go around a turn, roughly, I don't know, I guess it's about 30 miles per hour. 30 miles per hour. The radius of curvature is 50 meters, okay? And there's G, it's always 9.8. How much traction do I need to go around that turn? Well, in good weather, that's easy, 0.366. Even on a slippery road, you're probably going to get up to about 0.5. So even if the road's wet, I'm okay as long as I don't hydroplane. If it's an icy road, my coefficient of friction could drop to 0.1. So that's not going to be enough to make it. All right. And of course, on a dry road, I can actually even go faster. My coefficient of friction will be like 0.8 or be 1. If you ever hear your tires squealing on the road, okay, when you're going around a turn, you are beginning to go into a skid. Those tires squeal when you've reached just about the maximum of static friction, okay? That's not a good thing, all right? If you hit a slight bump and you already lost, some of your traction, you can go off the road and go into a ditch or worse. So again, you can find the frictional force. Mu is equal to v squared over r. G for the coefficient of friction at least, or you can find the maximum velocity that you need, okay? Or I'm sorry, not the maximum velocity that you can go around the turn for a given coefficient of friction. So the greater the coefficient of friction, the faster you can go. The larger the radius, and remember, a larger radius means less curvature, the faster you can go. And again, centripetal force makes it feel like you're being pushed to the outside. The actual force is the car is pushing you toward the inside. You feel like you're being pushed to the outside because you're pushed up against the car. That action-reaction effect. Okay, let's do a bank turn. You'll notice that many of the turns in the highway are banked, and this keeps it safer at higher speeds. So as you're going faster and faster, you need more and more centripetal force to make it around that turn. Well, by banking the turn, that points the normal force toward the center of the curvature, that makes some of the normal force add to that centripetal force. So not all the force has to come from friction. Now, in this case, we're going to completely eliminate friction. We're going to say, okay, the Daytona Speedway is banked at a 31-degree angle. You never get that on the highway. It's a really steep bank. Its radius of curvature is 316 meters. what would the maximum speed I could go without using any friction and still stay on that track be? Okay. What would it be if, let's say, there was an oil slick and my coefficient of friction went almost to zero? How fast could I go and still stay on that bank turn? Well, it's surprising. You can go quite fast. Now, the first thing that you're going to do is you're going to calculate a relationship between the centripetal force that you need to stay on that track, the normal force, and of course the weight. Okay. Again, we got no friction here. If we did this with friction, it'd be a little more complicated. Friction would add an extra term right here. But here, notice I've lined up my x-axis with the direction of the centripetal acceleration. The normal force is banked at some angle, and weight, of course, is down. I just need to calculate FC. So in fact, if I can calculate the normal force and just take the x component of the normal force, that's all my force. Okay, so the normal force and the weight equal the centripetal acceleration. But remember, the weight is just in the y direction and the centripetal force is in the x direction. So I just need to get n of x there. I don't need the whole thing. So I resolve my vectors. Here's n of x. And remember, this is an inclined plane. Our angles with respect to the y-axis, so x goes with sine here. Okay, normally x goes with cosine. So I get my sum of the force in the y direction. Normal force in the y direction pulls up, weight pulls down. And this just shows me the normal force for an inclined plane. It's mg over cosine theta. Okay, we've done that before. Now I did my force in the x direction, and this is not going to be zero. The sum of the forces is going to be mass times the centripetal acceleration. Okay, so it's mass times v squared over r. The normal force, an x, is now equal to that. So nx is this term. Here's our centripetal force equation. So there's my normal force. All right. And if I plug in just all my different values for the normal force, I can actually see what the centripetal acceleration is. Here's my equation from the x direction. Here's my equation from the y direction. I set these two equal to one another. That gives me the centripetal acceleration. Notice I had sine over cosine. Sine over cosine's tangent, so I can just say AC is equal to G tangent theta. And there, going around that bank turn, the maximum acceleration I can have without going off the turn is 5.89 meters per second squared. Well, what does that mean in terms of speed? I just plug that back into this equation right here. I know my acceleration, I know R. I calculate this and wow, I can go almost 100 miles per hour. That's about 90 miles per hour and still stay on that track, no problem. Okay? Now, if you use the frictional force, obviously you can go a lot faster.